A golf ball is projected horizontally off a horizontal cliff with a speed of 30 meters per second and lands 60 meters below sometime later. So we have to determine the ball's velocity just as it reaches the ground. So let's first visualize. I'm going to specify coordinates, right as positive, up as positive y, and then I'm going to draw a diagram. So I'm going to start with x and y axis, and that is the cliff. And now I'm going to draw a line diagram to represent the trajectory of the projectile. It's going to land 60 meters below the launch point. And initial x velocity, v naught x, and initial x position 0, initial y position is also 0. And final x position is an unknown, and then final y position is negative 60 meters because it's 60 meters below the launch point. And then let's identify the knowns and unknowns. Time is the only scalar quantity and it's common for both directions. And let's see the unknowns in x and y directions. So initial x position is 0, final x position is an unknown. Initial y position is 0, final y position is negative 60 meters based on our coordinate system. And initial x velocity is equal to final x velocity. It's 30 meters per second as acceleration is 0 in x direction. Constant non-zero velocity in x direction, and in y direction initial y velocity is 0 because initially there is an x component for the velocity. You launch it horizontally. Final y velocity is an unknown. And then acceleration in y direction is 9.8. It's negative based on the coordinate system. The object is in free fall. So acceleration downwards is 9.8 meters per second squared, and if you look at the horizontal velocity, it's not going to change at all. It's a constant throughout the motion. So the velocity vector in horizontal direction should have the same length because the magnitude is a constant. And the initial y velocity is 0. However, the velocity in y direction is going to increase at 9.8 meters per second every second because of the acceleration due to gravity. Now, if you want to calculate the velocity when it reaches the ground, you need to add the x and y components of the velocity. But it's not just the arithmetic addition. You have to add them as vectors. So you have to perform the vector addition. And now coordinates are specified, and then we need to solve for the y component of the final velocity. It's measured in meters per second. Final y velocity is negative because it's going down, and it's downwards. And then we have to solve for the velocity when it reached the ground and measured in meters per second. And a positive or a negative sign is not a clear way to indicate the direction for the resultant velocity. We need to complete the vector triangle, and then the angle should be calculated. Let's see the applicable concepts. This is chapter 3 in your textbook, 2D kinematics. Actually, this is 3.4. Okay, so now let's see, if there were no gravity, the object would actually continue in motion with 30 meters per second in horizontal direction. In actuality, gravity causes the ball to accelerate downwards at 9.8 meters per second per second. This means vertical velocity is changing at 9.8 meters per second every second. Now let's plan the solution. Let's look at the equations for the x and y direction separately. So for the x direction, we only have x is equal to x naught plus vxt. And for the y direction, let's look at all the possibilities. So first equation in y direction, y velocity, vy v naught y plus ayt. We do not know the final y velocity. We know the initial y velocity 0. Acceleration is a known and time is an unknown. So too many unknowns. Let's look at the second equation. And in this equation, so we do know the final y position. We know the initial y position, initial y velocity, time is an unknown, and we know the acceleration. So this equation can be used to solve for the time. I'm going to keep it aside and let's look at the third equation. We have the final y velocity squared is equal to initial y velocity squared plus 2a final y position minus initial y position. So in this equation, we don't know the final y velocity, but we do know all the other terms. So this equation can be used to calculate the final y velocity. So that is one of the variables we are trying to solve for. So that is the equation we are going to use. Now we are going to execute the plan. We are going to use the equation in y direction, and our purpose is to solve for y velocity, final y velocity first. So initial y velocity is 0 because the projectile is launched horizontally, and acceleration negative 9.8 meters per second squared, and then final y position negative 60 meters, and initial y position is 0. And when you take the square root of 1176 meters squared divided by second squared, you should end up of getting it should be just Vy because you're taking the square root. You will get plus or minus 34.3 meters per second, the square root of meter squared, second squared meters per second. So I'm going to accept the negative answer. The reason is the object is moving downwards when it reached the ground. So based on the coordinate system, the down is negative. Now, I do know the x velocity and I have the y velocity based on my calculation. So I'm not going to show the negative sign here because the y velocity vector is downwards. It shows that it's the direction. And this is the vector triangle. I need to solve for the velocity and the angle. Now I'm going to use Pythagorean theorem to solve for the velocity when it reached the ground. I have to take the square of the two velocities, and then I have to take the square root of it. When I solve for the final velocity, I get 45.4 meters per second. Wait, am I done yet? No, I'm not done yet. I have to still solve for the angle because velocity is a vector. It has not only a magnitude but also a direction. Now I'm going to use a trigonometric function tangent to find the angle. Opposite is 34.3, adjacent is 30. When I solve for the angle, I get 48.8 degrees. This is below the horizontal. Horizontal is the x direction. By looking at the vector triangle, we can see this angle gives us the direction below the horizontal. Solution is complete. We solve for the velocity just as the object reached the ground, and then the sign of the answer is correct, and then it has the correct units, and then magnitude of the answer is reasonable based on the given height, level, and everything. And we visualized the problem. We started with the diagram. We looked at the variables in x and y direction separately, and remember we used the vector addition, very important, and we solve for the angle because velocity is a vector.